good. Thank you. Thank you very much, Deirdre. And I'd like to thank the Fields Institute for inviting me to give a lecture at this historic meeting. It's very exciting to think of what's happened in the last 100 years. And I think we will all enjoy this 6 days that we're going to lie ahead of us. So thank you very much. I am going to talk about a topic that Kumar mentioned, in fact, that really ran through much of Kumar's later words on the work of Robert Langlands, motives and automorphic representations. And specifically, what I would like to talk about is another conjecture or pair of conjectures that introduce a universal group, or rather a universal group for each of these two subjects. On the one hand, automorphic representations, and the other hand, arithmetic geometry. And the relation between those groups really represents a general reciprocity law of the kind that Langlands has conjectured. But the point that to me is very exciting is that these groups are in some sense quite explicit. So they are universal groups, but yet they are in many ways, they're large and pretty complicated, but in many ways they're really quite explicit. So it's they're of course conjectural, and but we hope that all of this, well, let me go on with further remarks to describe about what one would hope for these conjectures. But motives, let me start with motives. So these are pure motives. They were proposed by Grothendieck in about 1965, and they really have two roles. They are they're fundamental but hidden building blocks for smooth projective algebraic varieties. I recall that an algebraic variety is the set of solutions, let's say in complex numbers, for n algebraic equations in m variables. The most general kind of and least technical kind of geometry one might imagine. They're very hard to solve. That's the downside of them, but they are the foundation of what we could call really geometry. And excuse me, they also turn out, if the coefficients are rational numbers, they turn out to be a foundation of much of number theory as well. So on the one hand, motives, these are the algebraic varieties, these are the smooth projective varieties. Motives are hidden building blocks for these varieties. They were proposed by Grothendieck, and it's a little bit like, if you think of algebraic varieties as geometric objects, maybe like that compose the objects of everyday life. They don't really, I mean, that's a stretch, but if they do, then motives are kind of like the fundamental particles of physics that compose these objects of everyday life. And the point is that a motive can appear in many different algebraic varieties, just as a proton can appear in many different objects of everyday life, in the nucleus of atoms of everyday life. They have a more technical and really very closely connected property, conjectural. They are a universal cohomology theory for these algebraic varieties, which governs all of the kinds of cohomology that have been invented over the years: Bethe cohomology, de Rham cohomology, and then in Grothendieck's hands, L-adic cohomology, Hodge theory, and so on. Motives are supposed to be the governing ideas that underlie all of these cohomologies. Okay, so let me just make that try to make that slightly more explicit. Suppose we have two fields, F and Q. F would be given an embedding. It comes with an embedding into the complex numbers. Usually F is actually a number field, and Q is supposed to be the rationals. So I'll really think of them in those terms. And according to Grothendieck, we expect a semi-simple Q-linear category of motives, pure motives over F. That is to say, they come from algebraic, they're associated with algebraic varieties with coefficients in this number field F, with coefficients in Q. That is to say, we can think of the cohomology, like singular Betti cohomology, as with Q coefficients. Two kinds of coefficients, one for the algebraic varieties, these are a family of equations, and the other for the cohomology groups that are supposed to be part of them. That's F and Q. And so as such, they would come with two functors, one from the smooth projective varieties over F, and the other into this category, into this category of motives. That's maybe I should, that's where I am here. So these are supposed to, this would be a whole sum of the motives. These would be the net total of the fundamental particles, if we like, that compose a given algebraic variety. And so that's a formal functor that would come from algebraic geometry. And then another functor, which maps this category of motives to vector spaces over Q. That's like cohomology. It's like Betti cohomology. As a matter of fact, the composition of these two functors, that's going to go from projective varieties over F to vector spaces over Q. That would be the Betti, that is to say, the ordinary singular cohomology of these complex manifolds over there to vector spaces with Q coefficients. And it's this first arrow that represents the building blocks property of motives. And it's this second arrow that represents the universal cohomology of them. All right, so this is all conjectures. These were formulated by Grothendieck many years ago, 50 years ago, I guess, 60 years ago. All right, now this category, supposed category of pure motives, would be what's known as a Tannakian category, as this was Grothendieck's idea, as one of his many ideas, with a fiber functor. This means that it's like an abelian category, but it's got a vector space additional structure, and it's got a functor from itself to the category of finite dimensional vector spaces over Q. And Grothendieck proved a theorem that any category that satisfies those properties is the category, it's isomorphic to, or it's actually anti-isomorphic, to the category of finite dimensional representations for an algebraic group, reductive algebraic group defined over Q with a canonical mapping into this group itself into gamma F. I'll write gamma F for the Galois group of the algebraic closure of F bar over F. So this is just a general categorical theorem that Grothendieck proved that if you have a kind of category that he proposed his motives would be, you get a reductive algebraic group over the number field F. Now we know about those things. Reductive algebraic groups, that's like, there are Dinkin diagrams for these things. There is 4 infinite families and 5 exceptional ones. And now, so this proposed group is going to have to be given by components from these families. Actually, any given component would have to be repeated a number of times because there's additional data that's put into it. But it looks like it ought to have some pretty explicit formula. So my question is, what is it? What can it possibly be? All right, so now we'll just take a change altogether, and we'll say something about automorphic representations, which Kumar discussed. And these were introduced by Langlands in this letter, that famous letter that in 1967. Well, actually, automorphic representations had been studied a little bit before, but Langlands proposed these fundamental conjectures for automorphic representations in this letter to Weil. It's quite funny. Weil had a ferocious reputation. I'm sure that Langlands, even though he was pretty confident, I'm sure he must have been a little leery about sending a letter that reordered the whole mathematical world, in his opinion, to the great number theorist Andre Weil. So he added a sentence at the end of his letter by saying, I hope these might be of some interest to you. If not, you have a waste paper basket where they can be deposited. And there's no record as to whether they put them in the waste paper basket. I'm not sure. Originally, they may not have. They were so revolutionary and so briefly discussed in Langland's letter that I'm sure no one, even the greatest living number theorist at the time, would have been able to see perhaps what was in them. But after a few years, he saw, and he was very extraordinarily impressed with them, at least as the story goes. Excuse me. So anyway, an automorphic representation, I will just give an informal definition. There's a locally for every group G. I'm talking now about a reductive algebraic group defined over the field number field F. For every one of those, there's a locally compact group, the group of Adele, so-called group of Adels, and there's a discrete subgroup sitting in that. A discrete subgroup sitting in that, just the group of rational points. I'm going to give, maybe I would just say a word about this. This for people that do not work in this area. For people who do not work in this area, that's a bit of a stretch. This way this is set up. It's set up in this way to facilitate work, and everybody always works because this is the easiest way to write it down. But I'll just say a word about what these things really are. G is a group that's attached to what's known as a locally symmetric Riemannian manifold. It's a class of Riemannian manifolds that are rigid. You can't deform one to the other, unlike sort of general Riemannian manifolds. These locally symmetric spaces are a discrete collection of Riemannian manifolds. They that are attached, they're really arithmetic. They're attached to discrete subgroups of the group of automorphisms of them. They each would have a Laplace-Beltrami operator. That's an operator on a Riemannian manifold. It has a spectrum, discrete actually and continuous. But it also has a collection of operators that commute with the Laplacian. These are what are known as Hecke operators. And so it's a little bit like, I think you could argue that it's a little bit like elementary quantum mechanics, where the Laplace-Beltrami operators, like the Hamiltonian, and the eigenvalues of these supplementary operators that commute with each other and also commute with the Laplace-Beltrami operator, the eigenvalues of those things, that's supplementary, and I believe that physicists would call those momentum observables. But in any case, it's a very, despite the rather, for people not in the area, the rather Baroque notation, that's a very basic object to study. And an automorphic representation is, it's an irreducible constituent of this Hilbert space. This Hilbert space is interesting because it has both a discrete spectrum, that'd be like the theory of Fourier series, and a continuous spectrum, that'd be like the theory of Fourier transforms, but much more elaborate, multi-dimensional spectra. And the problem, but they're really quite down to earth, fundamentally, theoretically fundamental objects. The question is, what can you say about them? And an automorphic representation is then an irreducible constituent of one of these things, It can be broken into a restricted direct product of irreducible representations, pi v, over each valuation v of f. Really, these, if f is equal to q, which it often is, it's really v ranges over prime numbers. So we're talking about these local components are a way of wrapping up the eigenvalues, the eigenvalues of Hecke operators. So the Hecke operators are attached to different prime numbers, and for every prime, given an automorphic representation, then it's got an eigenvalue of the Laplace-Beltrami operator, but it also has eigenvalues of this supplementary family, infinite family of operators parameterized by prime numbers that commute with the Laplace-Beltrami operators. And those numbers, those supplementary operators have eigenvalues attached to prime numbers. And it's those eigenvalues that are the fundamental sources of this subject. They are the ones that are supposed to govern how number fields are organized, how they classify, how they might be classified, and more generally, how algebraic geometry arithmetic algebraic varieties can be classified. That's, in some sense, the essence of many of Langland's conjectures. All right. So, so these automorphic representations, Langland said more than just, well, I haven't really even described exactly what Langland's conjectures were, but he said more. He said that these automorphic representations should be governed by, even classified by much simpler groups, Galois groups, for example, local Galois groups, or the slight extensions that were defined by André Weil, and further extensions that Langland's proposed. So this diagram here, this is a collection of locally compact groups that are meant to be much simpler, in theory, than the automorphic representations they're supposed to classify. In any case, the top one are local objects, that is to say, coming from Hecke operators. They each have embeddings in the corresponding global objects up to conjugacy. And this thing, by the way, this these are Weil groups. Weil defined these around 1950. This LV, this is more recently, this is known as the local Langland's group, which is the Weil group if V is an Archimedean valuation and is the product of the Weil group with SU2. It's the so-called Weil-Deligne group if V is not an Archimedean, is a non-Archimedean valuation. These five groups here are very well understood. But what's not understood is this a mysterious thing in the lower left-hand corner. And we can call that the Langland's group, the global Langland's group, or we can call it the automorphic Galois group. This is not well understood, and this is what one of the two universal groups that I would like to try to describe, the other being its analog for not automorphic representations, not analysis. This is really, we're really talking about harmonic analysis here, and generalization, a vast generalization, say, of Fourier analysis, or spectral theory, the spectral theorem. All of those things are part of automorphic representations, but it's really a branch of analysis. And excuse me, what Grothendieck was talking about was geometry or number theory. So in any case, we're talking here about some sort of universal group, LF, that plays a role in analysis for trying to classify these automorphic representations. What is it? There's two ingredients to define this group, LF, and I won't they're not really hard to write down, but I won't do them in detail. There's two ingredients. One is an indexing set, that's up here in the top row, where G is ranges over a so-called quasi-split simply connected group over F. And C, which is a set of numbers ranging over almost all valuations, is a concrete datum attached to an automorphic representation, really a special kind of automorphic representation, a so-called primitive automorphic representation, pi of GA. And it's the Hecke eigenvalues, this extra data associated to this representation that goes with G. So there's one G in one of these data, and then for every one of these G's, there's a whole bunch of C's, a family of eigenvalues of Hecke operators attached to automorphic representations of the group G. And then the second thing, so these are things. These are things, so that's to be regarded as an indexing set. And then for everything in this indexing set, there is also an extension of the global Weil group by a compact, simply connected group, namely just by taking the complex real form of the complexification of the group G. Well, actually, the simply connected cover of the dual group of the complexification of G. So I won't define those things, they're straightforward, but it's a very natural compact, simply connected group that you can attach to one of these indices. And you can show that there's a simply connected, that there is an extension L sub C attached to one of these indices by a compact, simply connected group, an extent of the global Weil group. All right, both 1 and 2 of these, I've made them sound simple, and in some sense they are simple, but they are they involve very deep information about automorphic representation, the eigenvalues of Hecke operators, for example. But we put them all together by their existence actually depends on the so-called principle of functoriality, which is one of Langland's main conjectures that Kumar mentioned for their definition. It's the definition of what I mean by a primitive automorphic representation. A primitive, I mean an automorphic representation of G that doesn't come from any smaller group. The principle of functoriality tells you that there's a map from automorphic representations of smaller groups to automorphic representations of bigger groups. And primitive one would be one that is not the image of one coming from a proper smaller group. So that's just in sort of general terms what these things are. And so then the definition, how long do I have, Deirdre?
Well, technically until 10:20.
10:20. Well, I've got 10 minutes. We'll see what we can do in 10 minutes. So what you do is then for this indexing set CF here, you form the fiber product. Each of these groups, infinitely many of them, but let's say they're given by pretty concrete data. There's infinitely many of them. They each fiber over the Weil group. And so you take the fiber product over the Weil group, and the fibers of each of these things are compact, even though there's infinitely many of them. So this LF is then going to be a locally compact group, very big, but I like to think pretty explicit, a locally compact group, and it'll come with local embeddings. So the local Langland's group, and it'll map into the Weil group with embeddings of the local Weil group. And some of Langland's basic conjectures would say the following, that there's a bijection between automorphic representations. There's a bijection between irreducible representations of this group, locally compact group. It's going to have finitely dimensional irreducible representations. And these things should correspond to the basic cuspidal automorphic representations of the general linear group. So these are n-dimensional representations of this global Langland's group, which I'm trying to persuade you is quite explicit, if complicated. Finite dimensional representations of that to automorphic representations so-called cuspidal ones. They're the ones that really occur in the discrete spectrum of the general Lydier group, which is compatible with the localizations. And then second is a more general mapping from maps from this into an arbitrary group, or actually the dual group of an arbitrary group. And that should correspond, be isomorphic. Those things should be isomorphic to packets of representations, of tempered representations for any group G that's quasi-split from bounded global Langlands parameters to disjoint global L packets, whose union, it was the set of all such representations, all automorphic tempered representations of GA. So I won't go into the details of that conjecture. This is part of Langlands, or it's closely related to Langlands conjectures. And the point is that it represents a classification of automorphic representation, these basic things that we want to know, the drive, we believe drive geometry and number theory. It's the two is a more as a generalization of one. All right. Now that's the automorphic Galois group. That's a locally compact group. It's supposed to describe fundamental objects in analysis, spectral theory. And now we want to be talking about arithmetic geometry. And so we want a group for that. Well, we don't want a locally compact group. We're talking about arithmetic. So we really want an algebraic group for that. But there is a construction that one can do with the group LF, an analytic group, that it's not too complicated. You take a piece of it, and out of that build another group that's not a locally compact group, but an algebraic group. And so on the top row, we have the group I just described, the automorphic Galois group. In the bottom row, we have its analog, what we hope will be its analog, the motivic Galois group. And I'll just say the top row, these are locally compact groups. These in the bottom row are complex pro-algebraic groups whose representations, now finite dimensional algebraic representations, would parameterize motives. And this would be a fiber product. I won't go into the details. This is a group that's obtained from the Weil group. The Weil group's a locally compact group, but it's a group introduced by Langlands in the Corvallis conference that basically is obtained from the global Weil group. That's not a locally compact group, but rather a complex algebraic group. And its definition is a little complicated, but it's very, very important. And it plays the role of the global Weil group. It's an algebraic group. And what you do is you just keep some of the things in the fiber product of L of F. You keep the ones which are of so-called Hodge type. That means that for every Archimedean valuation V, and for every representation of the upper component into GLN, you would ask that the restriction of R to the subgroup C star, that's contained in the Archimedean Weil group, that is a Hodge structure. So I won't go into that, but it's a way to throw away the components in the product, the fiber product that created LF, throw away the ones that don't have any hope of being arithmetic. Just throw them away and keep the rest, the ones that are associated to Hodge theory. All right, so this would be a general form of the Shimura-Tanyama. Kumar called it the Tanyama conjecture. This has been a source of some debate over the many years that it's been studied. I'm calling it the Shimura-Tanyama-Weil conjecture, that for every motive is attached in a very concrete way by means of an modular automorphic representation to a modular form. That was the famous conjecture proved by Wiles and Taylor that in fact actually implied Fermat's last theorem. So this is a generalization of that to all motives, that every motive can be attached in the way that I described to an automorphic representation. Okay, more work is required on this. This conjecture. The motivic Galois group is supposed to be defined over Q, and I've described it, what it is, what would be its complex points. So I think it's possible to say what its Q structure would be, but that's important to be able to describe this, not just its set of complex points. And again, one would like explicitly to be able to construct the cohomological realizations of GF explicitly in terms of these families GC that go into the original set of data. Say, how do you get the Betty numbers? How do you get the Betty cohomology? How do you get the Durham cohomology? How do you get the L-adic cohomology, and so on? How do you get the Hodge structure from this group, that's supposed to be attached, that would be supposed to attach to this group? All right, so there's more to be done on this. This was all for projective, non-singular algebraic varieties. But if you write down a typical equation in polynomial equation in n variables, n equations in m variables with say coefficients in the rational numbers, it's not likely to be projective. That is to say, its complex points are unlikely to be compact, and it's unlikely to be non-singular. Its complex points are likely to have singularities. In other words, it won't be a complex manifold. And so that'd be the general one. And those things actually, if you start writing down algebraic equations, most of them are going to be of this worse form. But there's motives for them too, conjecturally. This has been much more complex, and it's still far from being settled. But they're called mixed motives, the things that would be attached to these not smooth projective manifolds, but arbitrary not smooth projective varieties, but arbitrary varieties. They're called mixed motives. And they're at the heart of many things in arithmetic geometry these days, and most notably in what are called the Bailenson conjectures, which attach special values of L functions, these automorphic L functions, or these motivic L functions that Kumar mentioned. Special values of them should be gotten in very concrete ways from motives, and perhaps we could hope these groups that we're talking about. For example, just as an example, you know that zeta of 2, the sum n going from 1 to infinity of 1 over n squared, that's pi squared over 6. And when I was a first-year calculus student, we studied calculus at Apostle, and he mentioned this, and he said it was a formula. I think he said that Euler, did he say that Euler finally proved it? Or maybe Euler couldn't prove. Did Euler finally prove it? But I thought, this is amazing. How can you get pi out of that? I've never seen anything, heard of anything like that. And you can do that for any even number. Zeta of 2, zeta of 4, that'd be pi to the 4th times something. But zeta of 3, zeta of 5, zeta of 7, they're not, nothing of the sort. And there are conjectures by Bailenson that at the very first step say what those are. It doesn't evaluate them as a quotient of pi squared, but it says exactly why they're not like that, and it gives a way of constructing them and conjecturally. And not just those, but all of the L functions, the zeta function is just one of a sliver of all of the L functions that you would get from automorphic representations or motives. And the Bailenson conjectures tell you all the values that those are expected to have at integers. So, but that would be mixed motives. So find an explicit, I'm running out of time, find an explicit conjectural formula for, so it's supposed to also have a motivic Galois group. It's semi-simple part, it'll be an algebraic group. Its reductive part is going to be GF, and then what's left by a general elementary theorem about algebraic groups, what's left would be unipotent, and it'd be the semi-direct product of those two. So you want to know what this unipotent radical will be. Find an explicit conjectural construction of its unipotent radical as a pro-algebraic group with an action of GF. So as I say, that's very closely related to the Bailenson conjectures, also the Birch-Swinnerton-Dyer conjecture. And one could wonder whether, I don't know the answer to this, but whether one could also have a corresponding extension of the automorphic Galois group. And finally, I'm just going to say a word about a topic that is going to have to be part of this, exponential motives. There's more motives than just the ones that I've defined. There are motives, I haven't talked about how you get periods from motives, but that's an extremely interesting subject. Pi squared over 6 is a period that you get from a motive, and there's a huge, beautiful theory about these things, how you get numbers, transcendental numbers, a countable family of transcendental numbers on which the motivic Galois group, or rather its rational points, acts like a Galois group. It's like Galois theory, but for transcendental numbers, a countable family of transcendental numbers, and those are called periods. But one number that you don't, and all the numbers you ever hope to calculate, any integral of any function, rational function, let's say, over a domain and many variables whose boundary is defined by rational numbers, any such thing is going to be a period, except for E or gamma. There's a bunch of them that you're not going to be able to get that way. And so there's an extended theory, supposedly, that would get the remaining numbers. This extended theory would, I think, probably be a basic part of fundamental physics. And it also plays a role, when you talk about periods, you talk about the part of periods are linear differential equations in one variable with regular singular points. As we learned about those in third year, I'm sure most of us did. And but then there's irregular singular points, and these exponential motives. It's a different definition of them, or an extended definition of them. That's due to where did I write their names down? Lots of work has been done on this, but there's a beautiful book, 250-page on the internet by Fressan and Yossen about this other family of more general family of motives. And so they would fit into this diagram that I did for the motivic Galois group. And it should have a motivic Galois group, an exponential motivic Galois group. What explicit construction, if there is one, of G tilde F, what would it be? Is there some automorphic version of it? And for this, you need a further generalization of Shimura-Tanyama-Weil conjecture, i.e. an exponential automorphic Galois group, LF, not LF, but LF tittle, some extension of that. What could that possibly be? And I had a page 13, which somehow I didn't, it didn't come through, or I lost it when I was making, having these made. So I have a conjecture, and it doesn't mean that I don't have confidence in it, that I have not put that page in. I assure you it was an accident. But the conjecture is that you'd get them out of automorphic. Well, we've used up all the automorphic representations to get the group for motives, but there's got to be something more that you can use. And there's only one, I haven't looked at the special cases, but there's only one thing, in my opinion, that it could possibly be. And it's generalization of automorphic representations where you take finite covers of the adelic group, GA, rather than GA over GF, you take a GA tilde, a finite topological cover of that. That's been studied quite a lot, actually, and the sort of main examples are by Berlinski-Deligne, so-called Berlinski-Deligne extensions. And so I mean, very little has been studied about the sort of Langlands program for these exponential, for these extended automorphic representations. And people seem dubious when I mention it, but so in any case, I think, I just think there's nothing else that it can be. Anyway, thank you so much, and enjoy the conference.